Good morning, eighth graders. We are going on to a new chapter in science today. We are going on to chapter 4.3, and we're going to be talking about simple machines. And this is perfect timing since we're talking about this in social studies right now with the Industrial Revolution and westward expansion of the United States. And there's a lot of people doing inventions or making inventions right now to make work a lot more efficient and cheaper to do. So we get things like the plow, we get things like the printing press, we had the cotton gin, we have the mechanical reaper that we're going to talk about. And so this influx of simple machines is making work in America a lot easier so that America can start an economy that is cheap to produce, but also efficient to make enough to sell. So we are on page 248 in our science books, and we're going to be reading about simple machines and inclined planes. So couple things to start. I'm going to share my screen, and we're going to get a whiteboard out so we can do some work together as we read. Some objectives we're going to be reading about. We're going to determine the effect of an inclined plane on work and force, and calculate the mechanical advantage and efficiency of using an inclined plane. Vocabulary. Inclined plane is a simple machine that has a slanted surface. So not like a plane, like one that you fly, but an inclined plane would be something that looks like this. And so you start down here and you're working up in order to get to a higher position using a plane, rather than just lifting whatever it is straight up. Okay. How have machines affected people's lives throughout history? How have they changed society? The invention of the printing press, for example, permitted books to be printed quickly and made possible for people to have their own Bibles. Before the printing press existed, books were written by hand. The train and the automobile ushered in a mobile lifestyle, and today the computer provides instant access to information and people all over the world. Thank goodness for that we're able to even do this now and have education while a pandemic goes on. History provides many other examples of machines. The plow is a machine that improves agriculture. The ramp helped the Egyptians build the pyramids. The wheel and the axle led to carts and chariots. All these things are machines, devices that make work easier by changing the force and distance or by changing the direction of a force. Whether you use a broom, a key, a door, a screwdriver, a knife, you are using a machine. Now, when we think of machines, we think of something that's powered by electricity or powered by gas or steam or something that needs a source of energy. But really, everything that we use that's outside our own body to help make work easier is a simple machine. Even something as simple as using a rock to leverage something to get it out of the ground, or a stick to try and pop something out of the ground, that's a simple machine. And we're going to see the extent of that as we move on to through this chapter. Since God created people in his image, they are able to be creative. Many inventive people have used their creative abilities to give the world a variety of devices. Some of these devices make life easier, such as cars and bicycles. Others just make life more fun, like roller coasters and Ferris wheels. The world is full of machines. Machines of all shapes and sizes, machines that perform all sorts of tasks. Most of these machines are made of a combination of only 6 simple machines. Some of these are so simple that they are not often thought of as machines. This list includes the inclined plane, the lever, the pulley, the screw, the wedge, and the wheel and axle. And so these are simple machines that we're going to be going over the next couple chapters and breaking them down. So today we're going to start with the inclined plane. An inclined plane is a simple machine that has a slanted surface. A ramp is an inclined plane. Ideally, a ramp does not change the amount of work that you have to do, but it changes the way you do the work. A ramp increases the distance over which you must do the work, but decreases the amount of force that you need to exert. If the amount of force that you need, if you need to pull a piano into a truck bed that is 2 meters off the ground, would it be easier to push the piano up a 10-meter ramp or to hoist it 2 meters straight up? Even if you would have to exert a force over a distance of 10 meters, pushing the piano up a ramp would be easier than hoisting it straight up because you would not have to exert as much force over the 10 meters. So if you think of it this way, if you have your piano, we'll make an upright piano. Okay, here's our piano. Would it be easier to lift that piano straight up onto a bed, or would it be easier to have a plane that you then push it up? Now, pushing it up that ramp does take an amount of force because you're pushing it up against gravity, but that's all going to be a lot easier than it is to pull it straight up. If the piano weighs 300 newtons, then the resistance force is also 300 newtons. So let's say this piano weighs 300 newtons. The work needed to lift the piano 2 meters, so we'll say this is 2 meters, would require 600 joules of energy. And the way that you would find that is you would do 300 times the 2 meters equals 600 joules of energy that is needed to get that up there. So that does not change, but we can change how that work is distributed. If you push it up a 10-meter ramp, 10 meters, there would be an ideal mechanical advantage, which is IMA, of 5. Using that advantage, and so how do we find that out? To find the mechanical advantage of an inclined plane, which is on the next page in the gray box. So you have mechanical advantage of an inclined plane equals length divided by height. So if you have the length of your plane by the height of the plane, 10 divided by 2 equals 5. So 10 divided by 2 equals 5. And that's where they're getting the 5 from. So it has an ideal mechanical advantage of 5. Using that advantage, 300 newtons, which we started with, the weight of our piano, 300 newtons divided by the ideal mechanical advantage of 5, only 60 newtons of force. So if you have the weight of your piano divided by the ideal mechanical advantage, you end up with 60 newtons. So 60 newtons of force would be needed. How much work would that require? Well, if we have our formula here to plug that in, 60 newtons times 10 meters, which would be work, 60 newtons times the distance, 10 meters, equals 600 joules. So we're still ending up with the same amount of work that we had up here by just lifting it straight up. The same amount of work would be needed to move the piano that distance, but the force would be more reasonable. The efficiency of this system is 100% because the output force equals the input force. An efficiency of 100% is ideal, but it's not really perfect machine because the resistance force of friction is missing. So on your piano, if you're pushing it up an inclined plane, you are going to have a level of friction as you're pushing it up. And so that does decrease the efficiency a bit. Friction always reduces the advantage, and because it works against motion, the force necessary to push the piano would need to be increased. If friction is taken into account and the input force increases to 80 newtons, So down here, if this increased to 80 newtons, the work required to push the piano would then equal 800 joules, because you're doing your 80 newtons times the 10 meters distance to get 800 joules. The actual efficiency would be about 75%, 600 joules divided by 800 joules times 100. And so this would be the equation for efficiency that we learned in the last chapter. So efficiency, remember, equaled the work input, or the work output, divided by the work input. So the work output would be our 600 joules divided by the work input, which would have been the 800 joules with the friction factor. And so 600 joules divided by 800 joules would equal our efficiency. And then we multiply that times 100%. So we get a percentage here. So when we multiply that by 100%, and with an IMA of 5 and an efficiency of 75%, the AMA is 3.75. The ramp actually increases the force by a factor of 3.75. So the amount of work is increased. All right. The use of machines necessitates a trade-off between distance and force. The inclined plane requires a greater distance, but the advantage is the reduction of input force. So although you do need more space in order to put in an inclined plane, the benefits are it does create less resistance and an easier way of getting your job done. If you think of a moving truck, if you were to lift the boxes straight up to put into the moving truck, you would have less distance needed, so you could back that truck right up to the house, let's say, and just lift straight up and put it in. But if you had something really heavy, all moving trucks have a ramp that you pull out, and yes, you would need to back or have that truck be farther away from the house, so you would have the distance for that moving ramp to have space to go from the truck to the ground. But it would be a lot easier to push those things up the ramp than it would to lift it straight up into the truck. The less slanted an inclined plane, the longer the distance over which the force is exerted. It requires more work but less force, which in turn increases the mechanical advantage. So what they're saying here is if you have a ramp that is long compared to a ramp that's going the same height at a shorter distance, your angle here is going to be less than your angle here. If you're going the same distance or the same height, and the longer your ramp, the more the mechanical advantage. The Egyptians relied on ramps to provide a mechanical advantage they needed to move enormous blocks of stone to build their pyramids. Escalators, launching ramps for boats, and mountain roads are examples of inclined planes. What other examples of inclined planes do you see? If you look up at the picture at the top, you have a picture of a mountain with a road that kind of zigzags all the way down it. So if you think of making a road on a mountain, if this is your mountain, and you want to get from here to here, going up a road straight up like this is going to be extremely steep and it's going to take a lot of effort to do that. But if your road did what's called a switchback all the way up to get to the top, your distance is a lot longer to get up that mountain, but you're not climbing straight up. You are now climbing at a much lesser resistance force because you're going at a less steep incline. So yes, you have to go back and forth as you ease your way up the mountain, but your resistance to get up there is going to be a lot less. If you think of it like Mount Washington, if you've ever been to Mount Washington, you can hike Mount Washington and it's a pretty steep hike, but you can also drive up Mount Washington. And in order to drive up Mount Washington, you have to drive on roads that look like these switchbacks all the way up to the top. And so having this advantage of an inclined plane helps create something that's more efficient. longer distance might take more time, but becomes more efficient in the amount of force needed to be exerted. All right, questions for today's lesson. Number 1, how is an inclined plane helpful for moving large loads? So for instance, think of our moving truck. So why would it be better to, if this is your moving truck and you need to lift a box up this way, why would it be better, rather than lifting it straight up, to have a ramp that you can push your box up into the truck? What is the advantage of doing that rather than just picking it straight up and putting it into the truck? And you can answer that in complete sentences. Number 2, if a 10-meter ramp that has a height of 2 meters, this is kind of like the example we did before. Here's your ramp. The ramp is 10 meters long, 2 meters high. So if a 10-meter ramp that has a height of 2 meters were replaced with a 15-meter ramp, so longer ramp, same height, how would that change the mechanical advantage? And what would the IMA be? Okay, so how would that change the mechanical advantage? Would that make it easier? Would that make it harder? Okay, and then go back to what our equation would be for ideal mechanical advantage. Okay, if we look back to ideal mechanical advantage, let's go back and find the equation for ideal mechanical advantage. So ideal mechanical advantage is if we do the original weight of the item divided by the ideal mechanical advantage. So if we go back a chapter, let's go back and look for ideal mechanical advantage. Okay. All right, I can't seem to find that exact equation. Oh, I remember. Ideal mechanical advantage is doing your length divided by your height. So ideal mechanical advantage would equal your height, or your width, length, 10 meters divided by 2 meters would be for the first one. Okay, so 10 meters divided by 2 meters would be 5. And so your ideal mechanical advantage would be 5. Now, if you were to do that by 15 meters, ideal mechanical advantage equals 15 meters divided by 2 meters. What is 15 divided by 2? We would get 7.5 meters. And so your ideal mechanical advantage would be increased because your length is increased. Okay, so ideal mechanical advantage is your length divided by your height. So the longer your length, you have the same height that you're working to get your object raised to. The longer your ramp, the more efficient your ideal mechanical advantage is going to be. All right, number 3. Would the longer ramp increase or decrease the work? Okay, what's our equation for work? Our equation for work, or you don't even need to do an equation for this one. So would the longer rate increase or decrease the work, and why? So would it be more effort to use the longer ramp or less effort than the shorter ramp? So would it increase the amount of work you're doing or lessen it? Or would the work be the same, but the force is different? Okay. And looking at that, the longer ramp would increase the work. The longer ramp would increase the work because the greater distance is multiplied by the force. Machines trade distance for force. Remember, we just read that. So your distance, you have to do a trade-off. Your distance is a trade-off for your force, okay? So the amount of work would be greater. You're pushing for a longer distance, so you're working more, but your resistance, the amount of force that you have to give is less, okay? So if you think of it, if you're pushing it up this smaller ramp and yes, your distance is less, but your force is greater. You have to exert more force in order for that to get up. When you add to your ramp length, yes, you have to go a longer distance, but your force is going to be a lot less because you're going at a lesser steep plane, just like we just talked about with the roads on a mountain. If you were to go straight up that mountain, your distance would be a lot less, but your force that you would have to exert would be a lot higher because you're going at a steeper incline. If you were to do a switchback road all the way up that mountain, your distance is a lot longer, but the amount of force that you're having to exert is a lot less because your plane that you're going up is not as steep. All right, number 4, if an inclined plane has an ideal mechanical advantage of 8, an output force of 160 newtons, and an input force of 320 newtons, what is the average mechanical advantage? All right, so let's look at this. If a plane has an ideal mechanical advantage, meaning no friction taking into play, okay, so ideal means the best case scenario. If your ideal mechanical advantage is 8, your output force, the amount you have to push, your output force is 160 newtons, and your input force is 320 newtons. What is the AMA? The average mechanical advantage. Okay, so if we do some of our equations, efficiency equals the work output divided by the work input. Work output divided by work input. Okay, so if we look at our work output, we have 160 newtons. Oh, then we need to time this by 100%. So our work output would be 160 newtons. Our work input would be 320 newtons. So we're doing 160 newtons divided by 320 newtons times 100. Okay, and when we do that out, when we do the math out, if we do 160 divided by 320, 16 goes into 32. How many times? 5. We get 0.5. And if we're multiplying that times 100%, we end up with 50%. Okay? Now, if we're trying to find the AMA up here, we're going to do the average mechanical advantage, and that's going to equal efficiency times our IMA. Okay, and if our IMA was 8, we're going to do our efficiency, which was 50%. So 50% times our IMA, which is 8. Okay, and so if we wanted to do this out, we would be doing 0.50 times 8. Okay, and we get 0, and we get 40. We move our decimal 2 places over, and it equals 4. Okay, so our AMA, our average mechanical advantage, would be 4. So ideally, the mechanical advantage without friction would be 8. But in all actuality, when we do it out and we put in friction as a factor, then our actual mechanical advantage, not average, our actual mechanical advantage is 4. So it's about half. Still helpful, still important rather than just doing it by force, but it is less with that friction taking into consideration. All right, number 5. How could the mechanical advantage in the previous question be increased? I'm going to let you think on this a little bit more. So how could our mechanical advantage down here be increased? What would we have to do in order to increase that mechanical advantage? How could you make it so that the friction is less, or that there's less force being exerted? What types of things could you do in order to make this greater? Okay, so think creatively. What things, if you're pushing something up a ramp, what things could be added to help make that a little easier? Is there something you can put under the object to make it slide easier? Is there something, making your ramp longer be helpful? So think of some of the things that you could do to make this work more efficient. All right. We do not have a lab today because you do not have Newton scales at home to be able to do the examples of the lab. But if you go on your emails I sent your parents, I did send a number of videos about simple machines. And so there's one on inclined planes and one on wheels and axles and one on pulleys and levers and screws, wedges. So if you go on and watch a few of those videos, that'll give you a better example and some hands-on examples of these types of simple machines. So take a look at those. Tomorrow we're going to go on to levers. And I wish we were together for all of this so that we could really do these labs together and try them. But that's all right. God has a plan. So enjoy the rest of your day, and I will see you later.